All right, ladies and gentlemen, welcome back. In this video, we are going to be diving into some continuations of algebraic reasoning with a specific focus of identifying and utilizing the reflexive, the symmetric, and the transitive properties. So let's first and foremost identify what they are. Hopefully, they're not brand new to you. They're actually properties that are introduced in algebra. But because of the nature of geometry and knowing why we are making the decisions that we are making, you have to kind of know a little bit more about these properties than maybe what your Algebra 1 teachers had mentioned to you. So let's think about the reflexive property first and foremost. The reflexive property is one of the most ones that we use as frequently as anything else. And think about what you notice in each of these three scenarios. A equals A, AB equals AB, a measure of angle A equals a measure of angle A. Like, what are you noticing in those three different scenarios? Well, hopefully you're seeing that the left side of the equation is the exact same thing as the right side. And that shouldn't be too surprising because think about where that term reflex comes from. Reflex is from that term reflect. When we think of reflection, we think of what happens in a mirror. When you look in the mirror, you get the exact same image back as everybody else sees in person. And so the left side of the equation is exactly the same as the right side of the equation. And we're really going to focus on using the reflexive property when we start looking at our triangle congruencies. And when we use triangle congruencies, what we try to focus on is, just going to do a quick example for you. If we see that we have a triangle, we'll call it triangle ABC, and if I split it down the middle, and there's a point D down here, I can use this in comparing the two triangles by saying BD is congruent to BD, which therefore BD is equal to BD as well. And so that's definitely going to be utilized a lot as we get closer into our triangle focus in our curriculum. But for right now, as long as you can kind of understand that when the left side equals the right side, that is called the reflexive property. The next one is our symmetric property. And as you can see, if A equals B and then B equals A, it's just reading the left and right side of the equal sign in reverse order. We know that it doesn't matter how you read it, from left to right or from right to left, it equals the exact same thing. The only time that you would use a symmetric property is, let's say that we're finishing off what we're going to learn about is called proofs. And let's say, for instance, they want the proof to be x equals 7, but somehow, some way you show 7 equals x. You would switch it at the end by saying x equals 7 because of the symmetric property. So that's how we would utilize it in some actual context. And the last one is our transitive property. The transitive property is the one that's probably the most used, and I've talked about this a little bit in class already, but if A equals B and B equals C, then A equals C as well. I call it the common sense property because it just makes sense to me. But you also think about it in terms of the law of syllogism. The law of syllogism says if P implies Q and Q implies R, then we can say that P also implies R, hence the transitive property. And in each of these scenarios, the same thing kind of happens. Whether we're talking about angles, segments, or real numbers, the same concepts work. So let's kind of look at how can we identify a couple of these. It says if the measure of angle 6 equals the measure of angle 7, then we make the conclusion the measure of angle 7 equals the measure of angle 6. What property of equality illustrates this statement? Well, let's think about it. All I'm doing is reading the equal sign from right to left instead of from left to right after the then. So that's exactly how we utilize our symmetric property of equality. All right, and what about number 8? All right, number 8 says 34 equals 34 degrees, okay? Well, left side equals the right side, exactly as we see. There's that reflection in the mirror, so that is our reflexive property. And last but not least, we see the measure of angle 1 equals the measure of angle 2, but also the measure of angle 2 equals the measure of angle 5, so 1 also equals 5. If A equals B and B equals C, then A equals C as well. That is how we utilize our transitive property. All right, so that's kind of the basics behind it. Let's dive into a more application-based, what we call a show me problem, to really see how we can utilize a couple of these examples here? Well, what I want to do is I want to turn this into what we call a proof. Now, this will be the first proof of the year. And so a proof just basically, I'll give you the full definition in a later video, but a proof in general is just a statement that needs to be proven using deductive reasoning. And so we are going to prove that based on what is given to us in this diagram, that in fact dBA equals EBC. Measure of angle dBA is equal to the measure of angle EBC. So we are going to do what we call a two-column proof. And again, you're going to get some more definitions on this, but a two-column proof puts the statements on the left-hand side and the right-hand side is our reasons for making the statement. So let's see what we are given right off the bat. Well, we are given that angle 1 is congruent to angle 3. So that's information that we know. So we're always going to start with what is given to us. So angle 1 is congruent to angle 3. All right, then you want to ask yourself, what does it actually mean for 1 to be congruent to 3? The fact that those two angles are congruent physically means that their measures are the same. So that means that the measure of angle 1 equals the measure of angle 3. And why do we know that? Well, we know that because we know the definition of congruent angles. We physically know what the definition of congruency is. That's what allows me to say that they are equal to one another. All right, let's go back to the diagram. What are we trying to prove here? I'm trying to show that DBA, what I'm going to mark right here, this angle, right, is congruent to EBC. I'm going to mark it with a double angle over here as well. So I'm trying to show those two angles are congruent. Well, think about it. You have to start introducing these angles into your problem if you are going to show something about them in the end. So let's actually introduce them into the problem. What do you notice? Well, hopefully you see that the bigger angle DBA, measure of angle DBA, is really the measure of angle 1 plus the measure of angle, the measure of angle 2, measure of angle 2 plus the measure of angle 3. So that's what DBA actually is made up of. And then you ask yourself the question again, what physically allows me to make that claim? And I know that I can add the two smaller angles to equal the bigger angle because of the angle addition postulate. Sorry about the announcement. All right, so why is this important to us and why does this work? Well, look at what we've already claimed. We've already claimed that the measure of angle 1 equals the measure of angle 3. And we have a measure of angle 3 down here. But look even more so back to the diagram. The other angle, EBC, is the measure of angle 1 plus the measure of angle 2. So if I know that 1 and 3 are equal to each other, this provides me the freedom to interchange them at any time that I deem necessary in a proof. And so we're actually going to interchange them to say that the measure of angle 2 plus the measure of angle 1 equals the measure of angle DBA. And it means the same thing because 3 and 1 are equal to each other. So then you ask yourself, well, what allows you to make that claim? Well, I can substitute them out because 1 and 3 are the same. So I use the substitution property of equality. But now take a look at this, guys. Take a look at this. 1 and 2 equal dBA. But we've already said that 1 and 2 also equal EBC. So the measure of angle 2 and the measure of angle 1 also equal the measure of angle EBC. Again, why are we allowed to make this? Because we know the two smaller angles add up to the bigger angle by the angle addition postulate. But now take a look at what we've noticed here. Look at where my pen is outlining. I'm saying that 1 and 2 equal dBA, but 1 and 2 also equal EBC. If A equals B and B equals C, then A equals C as well. So I can make the statement that the measure of angle DBA equals the measure of angle EBC. What is it? Transitive property of equality. And that is how we determine an angle equals an angle using a two-column proof.